Before starting my talk, I say two or three things to you. The first thing is was here for the first time 25 years ago. More or less the aspect of this talk was the same, and now maybe some different portrait here concerning local leaders of the revolution, before the revolution and so on. But the rest is completely the same. It's very pleasant to be here again. Thank you for the invitation. Second is now is 51 years after the publication of Alexander Tsiolkovsky's theorem. In 20 years, around 20 years, we celebrate another conference in Murcia for the 30 years after Tsiolkovsky's theorem. Now 51 in this case. I think Tsiolkovsky's theorem has good health, so continues being good health. My congratulations to Alexander for this. The third thing is just to say, here, you have this date here, but this is false, it's not the case. Because a university is only 100 years old. Now we are celebrating this. But at this time appeared something like a college or something like this, but nothing concerning a university. Otherwise it would be the oldest university in all of the world. And here is one very old king of our country, Alfonso X. It's important in our country. Okay, and my talk will be devoted to this type, exactly Thue-Morse system of difference equation. Now I'm trying to motivate what the origin of this equation, this system, because it's connected with interesting things, very interesting things. Okay, as initial motivation is during years we have tried to understand the two-dimensional dynamics. Well, what is the secret, we can say, of two-dimensional dynamics? Exactly given a dynamical system composed one phase space, it could be R2 or even a compact subset of R2 on a continuous map. Of course, the main aim is to know the behavior of orbit of all points in this space. That's mean this P, one point P, FP, and so on, the iteration. I'm not going to turn this definition. Okay, but we try to understand what is the behavior of all orbits or all points in the phase space. Or is possible trying to evaluate the complexity of the orbits. That is the main aim. For example, interesting problem connected with this statement, initial statement, you have this transformation with two quadratic polynomials. Polynomial can be of higher degree, but okay, the problem is sufficiently complicated. And now we are concentrating this. Another example, particular example of this, we have some type of local Terra models translated from the different system of differential equation to discrete dynamical system. You can have these models. Okay, but there are another way of obtaining this type of transformation, two-dimensional transformation, when you unfold this type of difference equation, and xn plus 2 depends on the value of these two values before. Okay, if you unfold this, you obtain usually this type of transformation. Well, here two of them models of weakly Hawks, this one with 2 parameters, well-known Enon map with 2 parameters. You know this problem is very complicated. It has taken a lot of time to be able to prove that for some value, particular value of the parameter, there exists attractor, chaotic attractor, and so on. Okay, but now you have another line of producing this transformation, two-dimensional transformation. Imagine we have two sequences. We are constructing symbols, sequences of 2 symbols. Imagine we have 2 symbols, 0 and 1, and using a technique called substitution, maybe in another talk will be talking about this. We obtain we obtain transformation associated to these important sequences of two symbols. It will be Thue-Morse, Fibonacci, Shapiro, the generalization, and so on. Because there's a long list of transformation, I will concentrate only the first today. We concentrate on Thue-Morse case. Okay, what is the Thue-Morse sequence? The Thue-Morse sequence is this. You have this, exactly. But the meaning is, it says nothing at the moment, but it's the structure of this sequence. But this sequence is an ubiquity, mathematical. It appears in many fields, algebra, number theory, combinatory topology, and all that. Of course, was introduced by Balibrea, related, not problem related to number theory in 19th century, rescued then years after by the Norwegian mathematician Hassel, and as an example on a non-periodic sequence, but defined recursively. Okay, finally simplify the history of the problem. Morse proved that this sequence has an important property. It's overlap free. I try to go to this notion, overlap free. The introduction of Thue-Morse sequence can be done in the way I'm going to do, or many different or equivalent introductions. There are many. I concentrate only one. Okay, this is the introduction of this one introduction. Imagine can be introduced with a funny number of symbols. In order to simplify the things, I introduce only 2 symbols, 0 and 1. We follow the substitution rules we have here. The first symbol 0, and then blocks. This means blocks of symbols. We are producing blocks. X. Imagine that how to produce. If we have the block xn, which means n symbols, what to produce n plus 1. This is produced in this following way. Take the symbol in this block and put here the complementary, which means 0 is changed to 1, 1 to 0. Simple. And you obtain x plus 1. In this way, you can, starting at 0, you can continue and constructing this sequence, 0, 0, 1, so on. More complicated, more and more. If you continue, and so on, you produce one sequence. Simplify the things. Yes, in the product topology, this is the limit. Okay, you produce this sequence. This sequence we will denote it by T, small t. Okay. And there are another way of introduction to use the construction and to go through this problem. Okay, what is an overlap? An overlap for us will be a word. A word is a finite number of symbols. We call a word a finite number of symbols. But overlap is a special structure, which means one, okay, thank you. This is one symbol, only an individual symbol, 0 and 1, followed by a block of symbols composed of more than one element. This is the structure, overlap. For example, if we are in English, for example, and we use all letters, we have here the two words in the English with this structure, containing an overlap. These two words are alfalfa, this is entente, which are two Spanish words, but also adapted by English. And this contains this structure, because you have A, the symbol, and then the block is LF, and the same for the other one. Same. Entente. I'm aware you say is overlap free. That means does not contain this structure. Of course, it contains no word that is an overlap. For example, one example of this in one sequence, Thue-Morse infinite sequence. This is a well-known example of this without overlap free. It's overlap free. That does not contain this. And this property of this infinite sequence has important consequences. I'm going to try to explain briefly these consequences. Okay, for example, imagine we have the sheaf of two symbols, a metric space composed of all sequences with symbol 0 and 1, and with a metric, usual metric, in this case, and the shift mark. Okay, this Thue-Morse sequence T, the description of this in this dynamical system is an example of a uniform recurrent point. Recurrent point means that if you take any neighborhood of the element, there are an n, and if you iterate the map, in this case sigma, every time you come back to this neighborhood. If this is made in a more regular thing, you have a uniform recurrent.
You consider one side the shift or two sides?
It doesn't matter. But okay.
Extend.
Yeah, extend. Yeah. Okay. But in both cases it can be. Okay. How to prove that this T is a uniform recurrent point is not easy. It's not easy. You can find a proof of this in the Furstenberg book concerning dynamical system and number theory. And the proof is not easy, but okay, it can be proved that this is the case. This is a uniform recurrent. This is important because if you have a recurrent point and you obtain the orbit by the map, you obtain of course an invariant set, but also
what means synthetic?
Yeah, synthetic means that there are the distance. If you have one and the next one, the difference is bounded in all the series. it's a technical way to design this synthetic. I think it's a part of the proof of this.
Il tuo tempo in Sweden dove
Yeah. Okay. So it's another interesting thing is I'm not taking here the reference, but this you consider this sequence Thue-Morse sequence, and you consider the number represented base 2 of the symbols can be proved that is an irrational number, even non-algebraic. Okay, that is another property. Okay, and now I'm going to this. This is a physical part of the consideration. These physicians in 1992 consider an array of functional potential, which means in one direction you put some potential in these points of the same amplitude and so on. Okay, you receive one sequence of these, and the problem stated by this physician is from the electrical potential. Is the behavior of this is a isolator or is not isolator, or what is the degree of this isolation? It is necessary to technically define the problem. But as a consequence of this problem, okay, I'm not going to explain this because technically it's necessary using Redinger equation, then going to calculus and so on, this numerical calculus and so on. You can finally arrive to this in this obtention of this problem. For example, in another Thue-Morse picture concerning this, if you put here one type of atom and another different and so on, and follow the disposition, you receive a quasi-crystal structure, one-dimensional quasi-crystal disposition. Okay. Finally, we arrive to this system in this works in this paper, but as a system of difference equation, not a difference equation, a system to difference equation. Immediately, of the meaning of x and y n is concerning the trace sum matrix is associated to the problem, and so it's technically I left this explanation because it's very concerning the physical problem. Finally, we receive this equation, this transformation. This transformation from now we will call Thue-Morse transformation, T of S1. We can consider that this is defined in Turkey first. What is important in transformations is try to understand to look for topologically conjugate things to the first, because in this case you do this, you obtain several advantages, like periodic structure is kept, many dynamical properties are kept for topological conjugate maps in this case. Okay, now I will define this transformation. That this transformation is topologically conjugate to this. Also, this one is also topological conjugate to this. And here is the conjugation. In this case, it's easy to obtain this, but it's not the case. In general, the situation is not easy to obtain topological conjugation, topological conjugation. Okay. No, this, okay, one moment. Okay, this is connected with this is why I have the second way, the second form of the transformation with S, which is introduced by the physician and recuperated by Sarkozy in a conference in 1993. He proposed to study this transformation, and in fact he proposed a relatively interesting program of problems. Here there are part of this problem, but are the periodic point dense in delta. Delta was now in 1 minute I go to this delta. Is the restriction of the transformation to delta density? Is one of the border of delta now going to be an attractor in the minor sense, etc. There are some questions stated in this program.
So this map S is associated with the Thue-Morse.
Yeah, sure. In fact, is in the paper by this physician. They obtain this transformation, but also the other. But the other is, in my point of view, is easier to deal with. So we can use one.
I think it's not the
other.
Thue-Morse system per se, it's this potential.
Yes.
I mean, the Thue-Morse dynamics of the Thue-Morse system is very well understood. It's not an issue. But then you use this Thue-Morse to construct this potential. It's like Schrödinger equation with, say, a quasi-periodic potential. So it's a kind of derivative construction,
Yeah.
right?
Yeah. Okay. But again, yeah. Okay. Here we are using this the first form because it's relatively easy. The first thing is one would surprise that this triangle in the plane composed of 0, 0, 4, 0, 0, 4, these 3 points, you join this, and you have a triangle in the plane. This triangle is denoted by delta, capital delta. And it's important, in the inside, the interior of this triangle and of the boundary, because this triangle is invariant. So it's very interesting, and it's possible to prove, this is immediate, that the point in the interior has no preimages outside. So everything, the interesting part of the dynamic is concentrated in this triangle. And what's left, what happened outside the triangle, but what's happened outside the triangle is very easy, not complicated. But inside, yes, more. Yeah, we try to analyze this. But in the first form, but for some problem we will use this and for other this, depending on the problem. Okay. Here you have the first view of this. This okay, yes. Picture on it. Here. Okay, this is the triangle 0, 0, 1, sorry, 4, 0, 0. Here is the outside is very easy. Inside is complicated. Pardon?
The top is 0, 4.
Oh, sorry. 0, 4. Okay. This plane. Okay, and in this screen we have denoted this segment by gamma, capital gamma. Okay, so it's very easy to analyze what happened in the boundary. It has no problem, it's very easy. But what is important is that the quality of the situation of point 0, 0. This point is very important because there is an influence of inside of the triangle to the boundary through the point 0, 0. I mean the following, this is the idea is as follows. You are here to 0, and you consider this segment, you take point here, the set here, in the base. This point is going here or here, one interaction, for example, here, and then to here, and then to 0. All points. So this is the connection between the interior with the boundary through this segment and going finally to 0, 0. This 0, 0 is a fixed point. So it's absorbing, but also one point here has two images, one in this part and the other in the other part. And this one has another two images and so on. So there are many points going to here and then to 0, 0. Even was proved in the first paper by Bill that the union of these points is dense in the interior of the triangle. Okay, here you have a view of what's happening in the boundary. I continue. This one, I have commented this. Here, and you in order to see what can happen here. Imagine you choose this point here, is here, okay? This corner of the triangle. What happened? You have here one image. You have the point, the image, and the second, and so on. We have joined the 2 points in order to see something more. Otherwise, you have a spread quantity of points, isolated points, you can see anything. But okay, you observe some complication because it seems that the orbit with this point is going here, back here, but finally more or less concentrated in close to the base. Another mystery, what to do, what to happen. The same conclusion, only visual, nothing concerning mathematics, only visual, to see what can happen. Also another third, if you choose one point, but here in this corner, you have this. You have a density here, very density. Okay, this is a visual thing. This is the program, but okay, if we start to study this transformation, first periodic point. Periodic point, you start with fixed point. There are 2 fixed points only, of 0, 0, 1, 2. One in the interior and second in the boundary. But outside there is no fixed point. But the only with algebraic direct method. We will say immediately that is the only thing. Also using only algebraic iteration, and it's not difficult to see that outside the triangle we have no fixed point, but there are no 2 periodic points, neither 3 periodic points, neither in the interior nor in the outside. Okay, but at the first view it seems that there is no periodic point, but it's not true. There are periodic points. For example, using algebraic method of a resultant, you obtain that this one is a periodic point in the interior of period 4. Period 4. Just to take this and calculate the iteration and back for operation. Really, 10 minutes or 15 minutes, but it do you fail. Okay. Also, there are by other method, numerical method, you can prove that there is one periodic point of period 5, only one. And also by direct computation, also by random. That this one is a periodic series. It's a periodic point of your series. You can trace it immediately. But nothing more can be said if you don't approach in any way. Okay, here we have an important partial solution of the problem by the Slovak mathematician Malitsky that proved that maybe you can observe that in the base, when y is 0, you have the full parabola. So in the base, the dynamics of the transformation is the full parabola. So you have Tchaikovsky ordering and so on, because it's only one dimensional. But if you
Did you define delta? What is delta?
delta is the triangle.
What is gamma? What is gamma?
Gamma 1 was the cement, and gamma 2 and 3 was, I don't know if gamma 2 or 3, the other sizes of the triangle, even the intermediate size. This is most important thing. Okay, this interesting thing. If you have a periodic point in the base and you use the usual symbolic dynamic with two symbols, Malitsky proved that inside there are another periodic point of the same period mimicking the same symbolic dynamic, but adapted to the triangle and the left part of the triangle. The little triangle, you use 1, 2, or 0 if one point is there, or in the other part 1, 0. Okay.
So interior, what is interior of delta? Interior of diagonal or interior of the triangle?
The delta is, when I put delta is the total.
The whole triangle.
The total.
The whole triangle.
Yeah. Okay. You have this. So there are, he proved that there are periodic points of all period for n greater than 4. Okay. Here is the result, that's very technical. But okay, now in 1 minute or 2, some answering to Tchaikovsky problem. For example, the map is transitive, restricted to delta is transitive. But the proof is not easy, but instead of proving directly the transitivity, it's better using this notion of almost topological exact. I'm not going to the definition, but I will say what is topological exact. Given any open set in the triangle, there is exist one n in such a way that Tn of this open set is the total triangle. When this happens, this is totally exact. But there is a definition almost totally exact, so it's not exactly totally, but necessarily some approximation. But when you use this, it's relatively easy to prove that the map is transitive, because you prove that the transformation is here is almost topological exact, but this almost topological exact implies transitivity. Okay, this one thing. The set of period point is not dense in the triangle. The proof can be done in 2 ways. One way is using this decomposition of the transformation. See, if you use this transformation, G composed with 5 there's a coordinate change, but this is an interesting sometimes symmetric, 4 minus x and y multiplied by this and on the same in the second coordinate. To use this, it's possible to prove first that this map has a dense set of periodic points in the triangle, and the construction is very.
What is, I don't understand. what is G? G takes xy to what?
Yes, this is a
Just
scalar
scalar?
multiplied by one
Scalar.
vector. Okay, put here. The same multiplied by 2.
Sure.
Yeah. Okay. By this G, this is possible to see that the periodic point is dense. The construction is 1 minute more to say something here. Okay, you choose here 1 point, I'm going to there, and then this segment. In this segment, the restriction of this transformation to this segment is similar to the full parabola. So you can use the Charkovsky ordering, you have periodic point or order. Okay, it's necessary more explanation. So using this, you can prove that, of course, there is density of periodic point in the triangle, but not for R transformation, for T no. As a consequence of it, because this G, J, not J, this capital 5 is only, is not a conjugacy. It's not a conjugacy. If it were a conjugacy, of course, if one has a dense set of periodic point, the other, yes, they're the same, but it's not the case. So, not only this way, but using other things, you can do this. Okay, you have here some other additional things concerning. And now I'm show only pictures because we have understood some part of the dynamics, but the most interesting part is not understood yet. So it's necessary to work very hard here in order finally to understand what is happening exactly in the inside of the triangle. Here you have a decomposition, important decomposition inside the triangle. You have a point here, you are going here, and then you go for this region. But this is not the finishing to understand the dynamics. Here, just only one comment what happened outside. Outside is very easy. In one domain 1 is 1 point in domain 1 is going to domain 2 or domain 3, I don't know. Remember, okay, there is a secret. But finally, all points go to infinity. By iteration is very easy to prove that they go to infinity. And not in the same way, because when 1 point is here, the iteration is here, the iteration is here, and so on, is going to infinity, but in this way. But when the point is here, this part is also invariant, but the point is going to infinity in another way. So it's more or less is clear, some detail, but clear for say some thing. Okay, finally this picture. This picture is only approximately, only to see what happened. In this picture, only to comment, this 1 minute, is to we use color from blue until red, black, red, and so on, in the ways, the following way. Imagine you have, you take a grid of the triangle. You have a point here, and you follow its orbit, and you evaluate not all point, only 40 or so iteration or more. I don't know. Remember, but you calculate automatically, of course, the distance between the point and the first and second, and so on. This way is what evaluated, and depending on the evaluation, you put the color, the weight of color. For example, you can observe here is the fixed point, the interior.
I think you have 30 seconds.
Pardon?
30 seconds.
Yeah, sure. Less. So the fixed point is this color. Maybe it's not visible, but correct? It's color because it's fixed. There is no working. So you have an idea of what happened. Could happen. There are hyperbolic points, some type of stable and unstable manifold, so connecting one on the other. So it's necessary to do more work, very hard work here in order to finally to understand what happened. And the conclusion could be, my claim is that this is not exactly a tractor, but here there is a special maybe curve or special narrow stick in which is attracting not all point but part of the point, depending. Okay. This fact have to be clarified. Okay, thank you for your attention.
Any questions?
Did you compare your results with your discrete system with continuous one? Because local system is well known for continuous system. And did you compare your results?
No, but it's no
It's a totally
differential
different
equation.
story.
Yeah.
Differential equation. No, there is no.
It's absolutely.
No relation.
No relation. Oh, okay.
No, it should be something.
Maybe some-
Of
no.
course, this is a different thing, I understand. But
Yes. Okay, of course, local terra classical on difference theory equation, system of difference equation is clear. You have limit cycle, depending on parameters and so on. This is one word, but the discrete is another word. There are no connection. The only connection is a name.
Well, it's not a connection. There is a connection, but
Yeah.
the continuous time system is vastly more trivial.
yeah.
To understand that, go to one dimension
Yeah.
and consider the logistic equation. X prime is equal
Yeah,
to
sure.
xy, lambda x1 minus x. You only has two fixed points. When you go to the discrete model, you get all this,
Yeah. Yeah.
quadratic family.
Yeah,
The
okay.
same thing is here.
But
So it's
that-
vastly different
Yeah.
form.
It means that, okay, it's, maybe some connection, but
Formulas are similar, but the phenomena are vastly more.
Okay, have you seen something like limit cycles in your systems?
no.
No, also no.
How can it be if it's
Yeah,
topologically transitive?
because
No, it's possible. So,
It's topologically transitive, it cannot have a limit cycle.
maybe it
it's
is.
topological transitive.
But in general discrete system,
No.
for example, two-dimensional polynomial discrete system is possible to have.
Correct, but
Yeah.
topological transitivity is incompatible with limit cycle.
Yeah.
And they proved topological transitivity.
Okay. Okay.
In literature, is it published?
Yes, and there are, yes, I thought, okay, there are some lists. If I can, yes, one moment. I don't know. After the figures. Okay, you have some list now. All the literature, not all, exactly all, but most.
And maybe this question to Professor Sharkovsky, if in any of these books that are on standard, this program, Sharkovsky program is mentioned, do you know?
No, I don't know if it's mentioned or not. This program.
Is your program mentioned in any
No.
of these books that are in exposition? Ваша программа Шарковского, которая была отмечена, она в одной из книг там отмечена, которые на столе лежат. Ну ладно, потом. I have also a kind of remark relating my talk to this talk. So I didn't mention that behind the group, the examples that I give, there is some substitutions that I call Lysenko substitution. And this substitution originally was used by Lysenko to give presentation by generators and relators. And recently we started to study substitutional dynamical system generated by this. It shares many properties with Thue-Morse and other systems, but it is not primitive. And what is remarkable that now is very popular subject study of topological full groups associated with minimal contour systems, in particular system generated. They have some fantastic, very interesting property, in particular they act totally non-free, they are amenable, not elementary amenable. And what is interesting is that the group of intermediate groups embeds in topological full groups generated by this Lysionic substitution. And I raise a question that I propaganda people like Tarrant, for instance, Belisard, known especially Putnam, in substitution dynamical systems, they attracted this attention to this question. If topological full group generated by Thue-Morse system contains a suburb of intermediate groups. So it is known that it is amenable group, but if there are groups of intermediate groups inside.
I would like to point out that the symbolic Thue-Morse system and this guy are very different. This is
We understand, yeah, but
I think dynamic symbolic Thue-Morse system is minimal, right? And it's very different from this.
We
guy.
understand, but half of talk was dedicated to properties of Thue-Morse system. So
Yeah, but
I relate my talk to the first part of
That was
this
just
talk, not to the
motivation.
No, but,
second.
okay,
And for the second part, you mentioned Schrödinger operator. So in my Paris talk, there was a subject, the main subject was Schrödinger operator associated to Lysionic substitution.
Yeah.
The
No,
relation.
but the substitution is, for example, I have mentioned that this point we see in two space of two symbols is a uniform recurrent point. So if you take the orbit of this, you receive you have mentioned.
This is what
If you take the closure of the orbit of this point.
It's minimal system.
The minimal, sorry, it's minimal. It's minimal. So this is a generation of minimal, but in this space. But no, after this, the problem enters in physical interpretation, and then we go to a transformation related to this problem, and so on. Okay.
Yeah, and another
I
remark
think we
is
should continue the
Yes,
discussion
yes.
later because we are already behind the schedule.
Yeah, we can.